Warning: phenol and bromophenols are irritating. Bromine is toxic and corrosive. Hydrogen bromide gas is corrosive. Dichloromethane is very volatile. Work in a very well ventilated area. Hi guys, here is MH. Recently, I've decided to initiate my first ever photosynthesis project, the synthesis of adapalene. Now, this isn't just some quick temporary idea, but I've thought about this for nearly a year before today, went through tens of papers, and made a couple of very detailed plans. Adapalene is a third-generation retinoid medication used for acne, and I initially selected it as the target of my synthesis because the doctor prescribed it to me to cure the acne on my face, but that is another story. The second reason I chose to synthesize adapalene is that its synthesis is investigated and optimized by a surprisingly large number of papers, which means that each step in the synthesis is checked and confirmed by many people and thus less likely to fail. The synthesis is a four-step conversion pathway starting from 1-adamantinol and 4-bromophenol, which undergo a Friedel-Crafts alkylation followed by a phenolmethylation to obtain the intermediate. This intermediate is then coupled with methyl 2-bromo-6-naphthoate in a modified Negishi coupling to obtain the adapalene ester, which is hydrolyzed to afford adapalene. Sounds simple enough and high-yielding, right? Moreover, I realized that all of the precursors and reagents required in the synthesis can be obtained or otherwise made from domestic sources, so I designed this very large synthesis plan, starting from two common medications found in flu medicine, paracetamol and amantadine. Replicating this could be a future challenge for home chemists, but for now I'm just going to focus on the four steps that I mentioned to confirm that the method works and that my synthesis skills are qualified. But since 4-bromophenol appears to be easily prepared from phenol, I decided to make it myself. Of course, I still bought some 4-bromophenol from reagent companies to make sure that my remaining synthesis is going to work out. Anyways, let's get started. The patent I'm following gives the procedure of dissolving phenol in cold chloroform, dropwise adding a stoichiometric amount of bromine, and crystallizing the 4-bromophenol directly from the chloroform solution. But since I only have DCM, the solubility of 4-bromophenol will be different, and I'm not sure the product can directly crystallize, so I'm going to use more solvent and distill off the excess. I start by weighing out 9 grams or 0.048 moles of phenol that I made myself, and dissolved it in around 90 ml of DCM. The DCM doesn't need to be perfectly dry, but water interferes with the reaction selectivity to produce 4-bromophenol. The solution is then added to a flask immersed in ice water. I then made some bromine using 0.15 moles of potassium bromide, which corresponds to a 50% excess to my phenol. I'm not going to add all of the bromine in though. Note that I added some concentrated sulfuric acid in the funnel, so the bromine will be dry. The flask is transferred to a better ice bath, and I wait for the temperature to drop to 5 degrees C or below. The bromine is then added very slowly into the flask. In the reaction, phenol undergoes a typical Friedel-Crafts halogenation to yield 4-bromophenol. Now you may know that phenol reacts with bromine water at room temperature to give 2,4,6-tribromophenol instead. Indeed, the oxygen beside the benzene ring donates electrons to the ring and makes it more susceptible to electrophilic attacks, so phenol can be brominated 3 times. However, in less polar solvents such as DCM and at lower temperatures, phenol can be selectively brominated once. But halogenations usually yield a mixture of para and ortho products, and this reaction is no exception. It's interesting that the ratio of para and ortho products can be tuned by using different solvents. And yes, separating these two products is probably going to be challenging. They have very similar boiling points but vastly different melting points, so I'm thinking that a fractional crystallization can work, but that's for later. As more bromine is added, the mixture turns slightly yellow and the orange bromine color stays for longer. Hydrogen bromide fumes also start forming, and I place a beaker with ammonia solution to neutralize it. For larger quantities, it is necessary to install a gas absorption system. With a fan blowing beside the flask, you can clearly see the ammonium bromide fumes. 40 minutes into the bromination, the color of the mixture is persistently yellow, and after around 15 minutes more, it turned red. When the red color doesn't appear to fade away, I decided to stop adding bromine and remove the ice bath. I then lightly heat the flask to expel the hydrogen bromide and bromine, and also force the reaction to completion. As the mixture boils, a copious amount of hydrogen bromide is released, and the color of the solution slowly got lighter, eventually turning to a light yellow. The remaining DCM is then quickly distilled over. Since p-bromophenol has a relatively large vapor pressure, the flask is not touching the heating mantle to limit the temperature and prevent overheating, but I think I still overheated a little and the product looked like tar. I added some water and stirred it around, and fortunately the tar crystallized into dirty brown crystals. The mixture is filtered on a funnel, and some light brown solid is left behind, which should be our product, p-bromophenol. Although grossly impure, I'm still happy that I had some yield, since I used self-made bromo that likely contained water, and didn't calculate the amount of bromine to be exactly 1 molar equivalent. A few weeks later, I found out that a lot of white solids remain in my bottle of DCM when the DCM all evaporated away. I thought that this is also my product, so I ran a TLC with my first batch of product and a standard sample of 4-bromophenol. The result is rather disappointing, as the spot of 4-bromophenol didn't appear in any of the 2 other samples. I also performed a crude melting point test with some hot water, and only the pure sample of 4-bromophenol melted under 70 degrees C, while my samples did not melt. I highly suspect that my product was largely dibromophenol and tribromophenol, since I didn't control the amount of bromine. So yeah, this leaves us with a 0 yield. But this is the first video in my channel where a 0 yield can be confirmed. Before, I have no idea whether the substance I obtained is my target product, so a yield cannot be determined precisely, but now I can perform analytical methods such as TLC and melting point tests, and can know whether the stuff I have is the stuff I want. So this video actually represents a big breakthrough in my organic synthesis abilities despite having 0 yield. See you soon!